So far, we've introduced circular motion by talking about objects moving in horizontal circles. Now, in this lesson, we're going to kick things up a notch and talk about a couple of situations that are a little more sophisticated than that. We're going to talk about objects moving in vertical circles and also objects moving in situations where they have some forces on them that are sort of tilted at an angle compared to the circle that the object is moving in. Now, although these problems are going to look different than what we've dealt with so far, the fundamental ideas for solving them remain the same. We have our formulas for speed and acceleration of an object moving in a circle. Those are still going to apply. And if forces are involved in the question, we're still going to draw an FBD like we used to, and we're still going to use Newton's second law, F equals ma, just like we used to. So the steps for solving these problems are the same. There's just a few new ideas and new tricks that get thrown at you in some of these situations, and that's what we're going to go over today. So the first situation we're going to look at is vertical circular motion. So what I want you to kind of think about here is a scenario like this, where instead of, we have a person swinging an object, but instead of them swinging it horizontally in a circle that's parallel to the ground, like the hammer thrower we looked at in the previous lesson, this person is swinging the object vertically, up and down, around and around. Now, when we had the horizontal circle, there were a few nice things about that motion. The speed of the object remained constant the whole time it was going around a circle. And as a result of that, it had a constant acceleration. The direction of the acceleration was always changing because it was always going towards the center. But the acceleration always had the same magnitude. And the force on the object was always the same. Now, when we look at a vertical circle like we have here, things change a little bit. If you can imagine yourself in the same situation as this person here, who's swinging a key on the end of a ring, maybe imagine that instead of a key, that's something a lot heavier, a big mass that maybe weighs a kilogram. What you would probably notice is that the speed, unlike in the horizontal situation, is not always the same. As the object comes down, this way, it's going to be speeding up because gravity will be pulling it down. And as the object goes up this way, it's going to be slowing down. So we won't have constant speed. If we look at the force acting on the key, the centripetal force, the tension that pulls it towards the inside, that's also not going to be the same all the time either, which is also in contrast to our horizontal situation. You can imagine if you were spinning in this object, especially if it was quite heavy, when the object's up near the top, you might have a little bit of a break. The tension might not be pulling on you that hard. Whereas when the object's down here at the bottom, you're going to need a lot more tension in the string. Now, we'll talk about why that is, but for now, I want you to just think about this intuitively and see if that makes sense to you. If you can, go and grab a heavy object, attach it to a string, and swing it around in a vertical circle. I think you'll notice that when the object's up at the top, the tension's a little bit less. The string doesn't pull as hard on you. And when the object's at the bottom, the tension is more. Okay, so let's summarize these ideas. In a horizontal circle, like we looked at before, the magnitude of velocity, so the speed, the magnitude of acceleration, and the magnitude of the force are usually constant. In a vertical circle, like the one we just looked at, these quantities are usually changing. Now that complicates things a little bit, because when we came up with some formulas for centripetal acceleration, for example, one of the assumptions we used when coming up with that formula was we assumed that the magnitude of the velocity was constant. So if we're looking at a vertical circle where suddenly it's now changing, those formulas aren't necessarily applicable anymore. And so that means when we're looking at a vertical circle, like this one, we can't necessarily apply those same formulas all the time. While the object is moving upwards, it is slowing down, slowing down, slowing down, slowing down, slowing down, because gravity is pulling it down. And then while the object is moving downwards, it's speeding up, speeding up, speeding up, speeding up, speeding up, speeding up. So if we're slowing down on the way up and speeding up on the way down, when the object is right at the top, right here, there's a point where we transition from slowing down to speeding up. And that means at that point, right at the top, we're not slowing down or speeding up. We're switching from one to the other, which means at that instant, the speed is constant. Now the same happens at the bottom. Over here, we're speeding up, speeding up, speeding up, speeding up. On the other side, we're slowing down, slowing down, slowing down. So right in the middle, as we transition from speeding up to slowing down, there's an instant where we're neither speeding up nor slowing down. There's an instant where velocity is constant, where speed is constant. So that means although our formulas that we derived before that depended on speed being constant can't be used for this whole circle, they can be used if we're looking just at the very top or just at the very bottom. So there are 2 points in the circle where for an instant the speed, the magnitude of the acceleration, and the magnitude of the force are constant. And those points are at the top and at the bottom of the circle. So we still have a centripetal force and we still have a centripetal acceleration, and our formulas are still valid in a vertical circle, but only at these 2 points. So with that in mind, let's look at an example. Here we have a 1.7 kilogram object swung from the end of a 0.6 meter string in a vertical circle. We want to know the tension in the string, assuming it's going at 3.4 meters per second. But remember, we can only use the stuff we've learned so far at the top of the circle and at the bottom of the circle. Fortunately, those are the exact 2 times that I'm being asked about, at the top and at the bottom. If I've been asked to find the tension in the string over here, we need a more sophisticated way to look at circular motion that deals with cases where the centripetal force and the magnitude of the velocity are not constant. Okay, so let's look at these situations one at a time. If we look at the top of the circle, I'll do that first. What forces do we have acting on this object? Well, there's gravity pulling it down. And there's some tension in the string that's also pulling it down. And that's it for forces there. So let's look at Newton's second law. Remember, we were saying before, if there are forces involved in the question, draw an FBD, which we just did, and use Newton's second law, F equals ma. So let's dive into that right now. Okay, so if I add up the forces, I'm going to have Fg. And now remember, when we're saying direction, in circular motion, it's convenient to put a little star at the center of the circle. And we say anything going towards the center of the circle is positive. So FG is going towards the center in this case, so I'm going to put it as positive. Positive FG. And FT is also going towards the center. So I'm going to put it as positive as well. Then I take the mass of the object, and the type of acceleration we have here, because we're in circular motion, is a centripetal acceleration. Okay, so let's see what we have here. Fg is not given to me. Ft is the thing we're trying to find. The mass I know, and centripetal acceleration, I might be able to find that using one of my formulas. Remember, we have two formulas for centripetal acceleration. V squared over r and 4 pi squared r over t squared. In this case, I am given v, the speed, and I'm given r, the radius, so I think I'm probably going to use this first formula there. And Fg is just going to be equal to m times little g, so I can plug that in too. All right, if I rearrange this for Ft, I get this. And then I can plug some stuff in. And that gives me tension force is 16.1 newtons. All right, so now let's look at the tension force when it's at the bottom of the circle. Now remember, we were kind of saying that intuitively, if you actually picked up an object and swung it around in a vertical circle, and maybe you actually had the opportunity to try this, feels like there should be more tension at the bottom than at the top. At the top, you get maybe a little bit of a break, especially if you're not swinging it that fast. But at the bottom, the tension is really going to pick up. You'll feel a lot more pull on your finger. So let's see if that's maybe the intuition we have here. Let's see if that bears out in the calculations, and let's see if we get any insight as to why that is. Okay, so we're looking at the bottom of the circle this time. I'm going to switch to a different color. So we use blue for the top of the circle. We'll use green for the bottom. So let's again look at our FBD. At the bottom of the circle, I've got Fg going down. Should be about the same length as before, because gravity is still the same strength. And now I've got Ft, tension, going up. We think Ft is going to be a little bit bigger, but let's actually see. So right away, the difference here is at the top, Fg and Ft were working together. They're both positive. They're both going towards the center. At the bottom, Ft and Fg are working against each other. One's towards the center, and one is away. So one will be positive, and one will be negative. Okay. So, Newton's second law. F equals ma. I have Fg, but this time it's going away from the center, so I'm going to make it negative. And then I have Ft, again going towards the center, so it's positive. And because this thing is going in a circle, my acceleration is going to be a centripetal acceleration. Fg is going to be m times g. Ft, again, is the thing I'm looking for. And for my acceleration, I'm going to use, again, this v squared over r formula, because I have both of those values given to me. Okay. So rearranging this for Ft, I get the following. And subbing things in. Putting that through my calculator gives me an Ft of 49.4 newtons. So what we suspected might be the case certainly is. When we were at the top, we had a tension of only 16 newtons, but at the bottom, we had a tension of almost 50 newtons. So the tension is greater at the bottom than at the top. Now, why might that be? Well, at the top, like we said, we had Fg and Ft working together. So they were both positive. This meant Ft didn't have to work as hard because Fg was helping it out. And so when we solved for Ft, we had, and moved mg to the other side, it was negative, meaning it was making Ft a bit smaller. On the bottom of the circle, Ft and Fg are working against each other. So this Ft, first of all, it has to cancel out Fg, and then once it's done that, it needs to be even bigger in order to create an acceleration towards the center. So that shows up in the equation with Fg being negative over here. So when we move it to the other side to solve for Ft, it becomes positive, meaning that Ft now has to be a bigger number because of that positive mg term. Now, as a sort of an extension, let's suppose this object is being swung with just enough speed to keep it moving in a circular path. So we can go back and look at this, this drawing again we had over here. Imagine this guy is swinging the key just fast enough that it keeps going in a circle. So if he swings it too slowly, then it's going to come like this, and it won't have enough speed to make it to the top, and it'll probably do something like that. And if he swings it a bit faster, it'll make it up a bit higher, but maybe still won't be able to quite make it to the top, and it'll fall down like that. But if he swings it just enough, just fast enough, it might make it right to the very top. Now, what's happening at each of these situations? If the key takes this path here, it's because the tension in the string went to 0 at this point. The string would start to no longer be tight, and the string would sort of start to be loose and floppy. If the string follows this path here, that means the tension in the string would have gone to 0 at this point. The string would have been tight up until there, and then the string becomes floppy. So if we want the key to make it right to the very top, that means the tension can't go to 0 until right at the very top. So that indeed, if we're spinning something with the minimum speed we need in order to make it go in a complete circle, we have a situation where the tension is 0 right at the very top. If the tension is more than 0 at the top, we're spinning it faster than we need to. So, if we suppose the mass is spun with just enough speed to keep it moving in a circular path, then at the very top, we'll have a tension of 0, meaning the only force acting on it will be Fg, and Fg alone will provide the centripetal force, rather than Fg and Ft together. Now that's, remember, just for an instant. As soon as the mass gets a little bit past the top, when it's over here, the tension in the string will pick up again, the mass will have picked up some speed, and we'll have tension in again. So the tension's allowed to go to 0, but the only place where the tension can ever be 0 is right at the top. If the tension is 0 any other place on the way up, it will no longer follow that circular path. Okay, so let's take what we've learned there and look at a new situation, also a vertical circle, but no tension involved this time. A biker riding through a loop-the-loop with a diameter of 3 meters. What minimum speed do they need to have at the top of the loop not to fall? So by a loop-the-loop, I mean, a ramp that maybe comes down like this, and then there's a circle like that, and then the biker rides out the other side. So they have to ride upside down to get through this loop-the-loop. Now let's just look at the very top of the loop here. And let's draw a biker at the top. You know what, I might not actually try to draw the biker themselves, because that could get a little ugly. Let's just imagine they're there, and we'll draw the bike. So, obviously the worry here is if the biker is not going fast enough, they won't make it all the way to the top, and they'll do something like this and fall on their head. They need to be going fast enough to make it all the way around the loop, all the way to the top. So, forces that are acting on the biker. Well, there's going to be Fg acting down, and that's going to be going towards the center of the circle. And the other force acting on the biker is, well, between the tires and the ground, there's a bit of a normal force. And the normal force always acts perpendicular to the surface. So if the biker was over here, the normal force would be that way. If the biker was over here, the normal force would be that way. But at the top, the normal force is going to be down. Now, however, this is just like the tension in the last problem. If we want them to just go at the minimum speed they need to not fall off, we don't want them going any faster than necessary, then we don't want that normal force to be any higher than necessary. So it's allowed to go to 0, but only at the top. So in this particular situation, yes, for a bike going around a loop, there would be a normal force. But if it's just going the minimum speed it can to get around, the normal force will actually be 0. So let's look at this. I'm also looking at this problem now and thinking that 3 meters is a pretty tight diameter for a loop. especially if we want to fit a bike and a person inside it. But let's stick with it. So, remember, we've got a free body diagram, and we're going to F equals ma. So I've really just got one force. It's Fg, and I'm going to say it's positive because it's going towards the center of the circle. And I've got the mass of the biker, and because it's moving in circular motion, we've got a centripetal acceleration. Fg is going to be m times little g. And because I'm trying to find the speed, I better find a way to get speed into my formula. And the way I'm going to do that is by picking the formula for centripetal acceleration that has v in it, which is v squared over r. Now, you might have been worrying up to this point because nowhere in the problem does it tell us the mass of the biker. And here we see that's totally okay because it's going to cancel out anyway. So if I rearrange this and solve for v, I get v equals the square root of g times r. Because we're on planet Earth, g is going to be 9.8. And in this particular situation, there's a bit of a twist here. The radius of the loop is not this number. That's the diameter. Radius is going to be half of that. So the radius will be 1.5. Okay, so plugging through all of that, we get the speed this person has to have at the top of the loop is 3.83 meters per second. Now I want to talk for just a moment here about what sensations the cyclist would feel when they're on the top of this loop. At the top, we would actually say the biker experiences weightlessness. And this is a bit of a weird word. The word weightless sounds as if they have no weight. But that's not true. In fact, weight is the only thing we have. Weight, Fg, is the only thing we drew on the free body diagram. So why are we saying they're weightless if they clearly have an Fg? Well, the term weightless doesn't actually mean they has no weight. It means they don't feel their weight. So if you stand on a scale to measure your weight, you usually feel how heavy you are, right? There's some pressure on the bottom of your feet, and if you weigh a lot, you'll feel a lot of pressure. If you weigh a little bit, you'll feel a little bit of pressure. Your spine is sort of getting compressed. Your hands are being pulled down to your side by gravity. And you find you have to use your leg muscles a bit in order to stand up. So that feeling you have is of your own weight. You have a sense of how apparent your weight is. But it's not because you're feeling Fg. That weight you're feeling is because of Fn, the normal force pushing you up. If you were standing on your scale and suddenly the scale and the ground magically disappeared and you started free falling, you wouldn't feel your weight anymore. You wouldn't feel the pressure on the bottom of your feet. You wouldn't feel your hands being pulled down to your sides by gravity. You wouldn't feel your spine compressing, and you wouldn't have to use the muscles in your legs to hold yourself up. You'd be free falling. But you'd still have weight. You'd still have Fg pulling you down. What you'd be lacking is Fn. So although we basically always have weight, we only feel it when we're experiencing a normal force. So when we talk about astronauts up on the space station or in orbit being weightless, they're not weightless. They still have a lot of weight, maybe a little bit less than on Earth, but they have a fair bit of weight. What they don't have is any normal force acting on them. So when we feel our weight, what we're actually feeling is Fn. And as a result of this, sometimes we call Fn our apparent weight, the amount of weight we appear to have. And that's worth mentioning because we're now looking at problems where an object will feel a normal force, but it might be different at different times. On the way up, we said this cyclist will feel some normal force. At the top, the normal force will be 0, so they'll feel weightless. And at the bottom, or on the way down, they'll have more and more normal force again, meaning they'll feel heavier and heavier. Their apparent weight will go up. Okay, so that's some examples about tilted forces, or about, pardon me, vertical circles. Let's look now at another scenario of tilted forces. When cars travel at high speeds on highways, they usually don't rely solely on friction to keep them from sliding off the road. If a car is trying to go around a corner, right, we have friction pushing it towards the center of the corner. If the car hit a patch of ice, it would lose that friction and it wouldn't be able to do the corner anymore. So friction is crucial normally for going around corners. But if someone's designing a highway and they want it to be particularly safe, they don't want to rely on just the friction between the wheels and the ground to get a car around the corner. What they do is they take the corner and they make it banked. And this allows there to be another force that acts as a centripetal force other than just friction. Let's look at an example to sort of illustrate this. So here is a banked corner. We're sort of looking sort of behind. We're sitting on the road and we're looking ahead of us and we see the road surface here. And a car would be maybe driving into the page. And as we see, the road surface is at an angle. It's banked. So let's draw our car. We got a little license plate down here, some stuff on it, and a couple of brake lights. And of course our tires. All right, so there's our car driving into the page away from us. And again, I'm going to put a little asterisk over here to show where the center of the circle is. Now, force is acting on the car, right? Same steps as always. We're going to do a free body diagram, and then we're going to use F equals ma. No surprises here. So we have Fg acting down on the car. And that's going to be equal to m times little g. And we've got a normal force pushing on the car's tires. And normal force is perpendicular to the surface. I'm drawing normal force quite large, and there's a reason for that. Okay. Now, if we look at what's going on, normal force sort of has two jobs. In the y direction, straight up and down the page, there's got to be no acceleration, right? This car isn't going to hover off the ground and float up into the air, and it's not going to burrow down into the road. So we can't have any acceleration in the y direction. That means, and I'm seeing now that my normal force is maybe a bit too long, so I'll redraw it a tad shorter. So my normal force has a y component, and it has an x component. And because there can be no net force in the y direction, like I said, we're not floating into the air or burrowing into the ground, this component of Fn has to match this component of Fg. We're basically saying the sum of the forces in the y direction has to be 0. Now, I should actually add here the tilt on the roadway. This is what we're trying to measure in this question. The question says, we haven't really dug into the question yet, but it says calculate the angle at which the curve must be banked. So that theta is what we're going to try and calculate. Now, that theta, that angle there, which I can call theta, is going to be the same as this angle here. So I can also call that theta. And over here I'll have Fn times cosine of theta. And up here I'll have Fn times sine of theta. Okay, so if I look at the forces in the y direction, which we sort of already did, but I can kind of write this down. I know the sum of the forces in the y direction has to be 0. Therefore, Fn times cosine of theta has to be equal to mg. Okay, now in the x direction, that's where all the excitement is happening. The x direction is where the circle that the car is going in sits. So that's where I have my centripetal acceleration and my centripetal force. And indeed, this force right up at the top, Fn sine theta, is my centripetal force. This is my force that's going towards the center of the circle. That's my force that's causing all of the acceleration. So if we look at the x direction now, we have F equals ma. We don't have acceleration in the y direction, but we do have acceleration in the x direction. So here I'm going to have my force Fn sine theta, and it's going towards the center, so it'll be positive, equals the mass. And okay, at this point, let's maybe look at what the question's asking. So we want to know what this angle theta needs to be, so that if we're traveling a speed of 22 and the radius of the corner is 475, we keep moving in a circle. We don't slide off. So I got to think what formula I'm going to use over here for acceleration. I'm given a speed and I'm given a radius. So picking v squared over r makes a lot of sense. Now, before we dive into some math here, let's just kind of think about what's happening here. The idea is so you imagine you're a highway designer and you're designing this corner. Basically what we want is that if this car has absolutely no friction, right? Normally we would have drawn some friction. There would be, a force down here acting parallel to the surface. The friction on the car's wheels, pushing it sort of towards the center of the circle. But in this case, we said that it would be a frictionless curve, so we didn't draw that at all. So imagine a situation where we would have a frictionless curve as like if the car has hit a patch of oil or a patch of ice. And the job this highway designer has is to make it so that if this car hits a patch of ice and has no friction at all, it'll still keep going in a circle. And they can make that happen by choosing this banking angle. If the angle is not big enough, the car will probably, when it hits that ice, it'll probably drift up this way and off the edge of the road. If the angle is too steep, then the car will probably slide down this way towards the bottom of the bank. But if the angle chosen is just right, the car won't slide up or slide down. It'll stay at that same height, and this component of Fn will be just enough by itself without friction to keep the car in circular motion. So if we go to solve this, let's see. I have the speed I want the car to be going at. That's right here. I have the radius of the curve. That's right here. Theta is the thing I'm looking for, so that's fine. But I don't know mass, and I don't know Fn. So that's going to be a bit of a problem, except over here, when I looked in the y direction, I have a formula that has Fn and has mass. So what I'm going to do is I'm going to take this formula and I'm going to isolate Fn so I can sub it in to the other side. So Fn equals mg over cosine of theta. So then I can take that over here and plug it in for Fn. So instead of wherever I see Fn, I can write mg over cos theta instead. Okay, now I can see my masses are going to cancel out. That's nice. I know the V, so that's good. I know the R, that's good. But the issue I'm having now is that it's hard to isolate for theta because I have two thetas. I want to just have one so I can rearrange this and it says theta equals. Having theta in two places is tricky. But what you may recognize here from your math class is that sine theta divided by cos theta is actually something else. And here's a little reminder as to what that is and how you can remember it. So sine theta divided by cosine of theta. Well, sine theta is sine is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. This is just SOHCAHTOA we're using. Now, so here I have two fractions, and I'm basically dividing them. How do I divide fractions? Well, I do that by flipping and timesing. So opposite over hypotenuse, that's the first one. But the second one, I'm going to change it to times, and I'm going to flip it. So hypotenuse is on the top, and adjacent is on the bottom. Now I have a hypotenuse here and up here, so they'll cancel out, and I'm left with opposite over adjacent, which you may remember is tan. So sine theta divided by cos theta is equal to tan theta. And that solves our problem that we were having before. Here we had theta in two different places, so it was hard to isolate it. But if I replaced sine divided by cosine with tan, that problem goes away. I'm just going to give myself a little more space here. The V is going to be 22 squared. R is going to be 475. So all I have to do is take G, move it to the other side, and do inverse tan. And that should give me my final answer. So theta equals inverse tan 22 squared divided by 9.8 times 475, or theta equals 5.64 degrees. So if you are the person designing this highway and you give this corner a bank of 5.64 degrees, then even if it becomes frictionless and the force of friction completely disappears, there will still be enough of a centripetal force here from that component of Fn that the car will be able to continue going in a circle of a radius 475 meters. They'll still be able to make it around the corner, even with no friction. Okay, there's one more problem I want to look at with you guys here. And it is very similar to this one. A toy plane attached to a string, so it flies in a horizontal circle with a radius of 0.8 meters. The string makes an angle of 28 degrees to the vertical. What is its period of rotation? So, free body diagram. This airplane has FG going down. It's got a tension force in the string, and that tension force has a vertical component that has to counter FG and a horizontal component that's providing the centripetal force. Now, I want to show you another way we can look at this that's maybe a little simpler than what we did in the last problem, that still gets us this tan in our equation, but without having to go through kind of this mess down here and remembering that sine divided by cos equals tan. If we just look at this triangle here, this angle here is going to be 28, just like the angle that's shown. What I really want to do is I want to find the net force. Up here, we looked at the forces in the y direction. We looked at the forces in the x direction. That was all well and good. But what I wanted in the end was just the net force. So, net force equals ma. Well, I kind of know what the net force is going to be looking at my free body diagram. I know that this and this are going to cancel out. The airplane's not rising up towards the ceiling. It's not falling down towards the ground. It's staying at the same height as it goes in this circle. So those two are going to cancel out, meaning my net force will just be this guy. So if I can just find that length, I should be good. And I can sub that in right over here for net force. Well, because Fg is equal to mg, that means this component up here is also going to be equal to mg. That's kind of what we did in the last problem when we said the sum of the forces in the y direction was 0. So now, let's see what we can do with this triangle. I have a situation where if we're looking at this 28 degrees, I know the adjacent side and I want to know the opposite side. So I'm thinking, what trig ratio uses opposite and adjacent? Well, that's 10. So one thing I can say about this triangle is tan of 28 equals this guy, which is, we decided was my net force, divided by mg, this guy here. We could also call this, if you don't like the word net force, we can call this our centripetal force, Fc. Okay, so I could then rearrange this and say my net force, or my centripetal force, equals mg tan 28. So, plugging that in over here, remember, this guy we just found out was mg tan 28, and that is my net force, so I can plug it in on this side. Okay, so I still have the mass of the plane, and I need to pick a formula for A. Well, we're in circular motion here, so I have centripetal acceleration, so I've got those two formulas to pick from. In this question, because I'm interested in the period of rotation, capital T, I'm going to pick the formula for A that has capital T in it, which is 4 pi squared r over t squared. Again, we have this nice situation where I have an m on both sides. They're going to cancel out. And if I solve for t, I should get t is equal to, or t squared rather, is going to be equal to 4 pi squared r over tan of 28. And then because I want to get t by itself, I'm going to have to square root that whole thing. So the period of rotation is equal to 4 pi squared. R is 0.8 over tan of 28, which gives me an incorrect number, I'm just realizing, because I forgot about something important in this formula. I forgot about the g. I moved the tan 28 down here to the other side, but I did not do the same with the g. So let's do that right now. Tan 28 times g in the denominator. Tan 28 times 9.8. Okay, now let's see what we get. And I get 2.46 seconds. Okay, so looking at these last two questions, where we have tilted forces. In this case, it was an Fn, kind of tilted towards the center of the circle, but not pointing straight there. Here it was a tension force, tilted towards the center of the circle, but not heading straight there. How do we tackle these? Well, it was pretty straightforward. In both cases, we did a free body diagram, and then we used F equals ma. In this case, we used it in the y direction and the x direction separately. We said in the y direction there would be no acceleration, and in the x direction, that's where we had centripetal acceleration. And in this situation down here with the airplane, rather than looking sort of at x and y separately in our formulas, we just said, we know there's going to be a net force towards the center of the circle. We know that these two are going to cancel out, so the net force will be that. And we just plug that directly into F equals ma. And basically we just sort of looked at the x direction because that's where everything was happening. In both of these equations, we ended up with a situation where the m's canceled out. So if you're ever looking at a question and you're like, I don't know m, that's going to be troublesome, stick with it and you might get to a situation where they cancel out. Although in the second question, it wouldn't have really mattered because we were given m anyways. So I maybe did a little more work than I had to. I could have just plugged that in and got a number for m, or used that as a number for m right away. Now in both of these situations, we ended up getting a tan was involved somehow. In the first situation, we kind of found our tan by, again, working in y and x separately, getting a cosine on one side, a sine on the other side, and then remembering that sine theta over cos theta is equal to tan theta. In the second part, we kind of got our tangent by just looking at this triangle directly and saying, well, the side we're interested in is this side, which is the opposite side, and because I know the adjacent and the angle, I can use tangent to find that side directly, and we didn't have to get sine divided by cos or deal with anything like that. So when you get one of these problems, do a free body diagram, break it into components where necessary, use F equals ma, and you'll maybe want to look at what's happening in both the y direction and the x direction. And then have hope that m will cancel out if you're feeling like you don't know what it is and you might need it. And remember that in addition to just using sine and cos, tangent is also a tool we have.